All right, before we get into new material, I thought it would be worth a few moments of our time to review some of the basics of introductory econometrics. And in so doing, we'll also introduce some new notation for familiar concepts using matrices. So we'll call this Lecture 1B or Lecture 1A, just kind of went over the syllabus, etc. So we'll look at, like I said, a review of topics, an extension of some of those topics, and delving back into using and reading output in Stata. So thought we would look at an example here. And you could use use this as inspiration, as it were, for your product or for your project topic. But kind of a classic development question: how effective is international aid in mitigating poverty? Right. So poverty would be our dependent variable. Our key, what we would call our treatment variable, our X variable of interest, would be the level of aid received by that country. And we might also control for education. If this was an actual thesis topic, you'd want to have additional control variables, right? Something we'll remind ourselves of later on. But this is a multiple regression model. And just remember the notation, right? So the sub I indicates an index, in this case, of cross-sectional units, which would be country level data. And then we have our linear equation used ultimately to predict the level of poverty as a function of education spending and international aid. So just to break down the notation again, this should all be familiar, but keep in mind that B0 parameter, that is our constant, our intercept. Technically here, it would be the predicted level of poverty in country I if their education spending and aid received were both 0. So unlikely to be a realistic outcome, but that would be our starting point for prediction on poverty. The B1 and the B2, those of course are the slope or marginal effect parameters. And here, because it is a multiple regression, we would treat those as partial derivatives, right? So the B1, the impact of a 1-unit change in education on poverty holding aid constant. B2, the impact of a 1-unit increase in aid on poverty holding education constant. And don't forget about that error term, right? So that U sub I, that would be for each country, the level of poverty that we see in the data that cannot be explained by education and aid. So that's either going to be random variation, or of course, in this case, because we have a fairly small model, that's going to be level of poverty explained by other factors that we haven't included, we haven't controlled for. So what we should be doing, right, before we get any data and run any regressions and get any results, is thinking critically about this process, this model, this equation that we have as our econometric approach, meaning we would want to think about how the classical regression assumptions apply to this particular model. And again, this could be a 2-hour lecture on its own, just going back over what all those assumptions mean, their implications, and all the testing associated. But just as a quick reminder, when we think about our assumption number 1, what we would call the specification assumption, right? Meaning we got it right, that the equation that we are estimating contains all the relevant explanatory variables and in the correct functional form. So here we have a linear function relating aid and education to poverty. That's an assumption that we're making. Does education have a diminishing returns effect? Does aid have an increasing returns effect, diminishing returns? We're presuming that's not the case, right? And then likewise, we're clearly violating this assumption because poverty is going to be a function of a lot of other factors besides education and aid. So we're already in bad shape there. But just as a reminder, that's what assumption number 1 dictates. Number 2 Assumption number 2 is largely theoretical in nature, difficult to test for. It's that the center of the distribution, the average expected value of the error term for each observation is 0, which we could think of as, consistent with that error term being a purely random outcome for each country across repeated samples. Now things get a little bit trickier, still in the realm of thinking about the properties of that error term. Assumption number 3 is that every explanatory variable is entirely uncorrelated with the error term. So in this case, education and aid should be uncorrelated with the error term. If this is violated, recall, we're going to end up with biased coefficients, and we're going to spend a lot of time this semester dealing with that assumption 3. But again, at the basic level, we can think of it as consistent with a purely random error term. It's uncorrelated, unpredictable based on other outcomes. Assumptions 4 and 5, still thinking about those error term properties. Assumption 4 is the zero autocorrelation assumption, which in this case means that the random level of poverty in one country will not be related to the random variation in poverty in another country, meaning we're not expecting any spillover effects, which, when we put it that way, somewhat dubious assumption in this case, that if something causes a high level of poverty in one country, it's probably going to spread to its neighbors, either physically the nearest neighbor countries that share a border or those that share trade flows or capital flows. But that's the assumption. Error term random, therefore uncorrelated with any other outcome within the sample. And then number 5, the no heteroscedasticity assumption, meaning that the variance of that error term is going to be constant. Every country's random variability should have the same scale, the same level of dispersion. In notational terms, we would say that the variance of every observation of the error term is the same value, that sigma squared value. Number 6, we are in good hands here. That is the no perfect multicollinearity assumption. So none of our x variables are perfectly predicted by any combination of other x variables. Here, all that means that education spending is not a perfectly linear function of the level of aid. They may be related to each other, probably negatively, but we certainly wouldn't expect a perfect predictability. And then that 7th assumption, easy to make the assumption, difficult to prove in practice, would be that normality assumption that we will need for hypothesis testing. So the error term for each observation follows a normal distribution. Okay, so again, we're not going to delve into all of these in great detail, but they're always lurking in the background, right? Some of these are going to bubble up in certain circumstances. Mostly it's going to be that assumption 3 that's going to be a concern for us. So before we get into looking at some data and reminding ourselves how that's going to work, this might be an opportune time to introduce some of those same concepts, but in the purely mathematical formation of matrices and vectors. And truth be told, the more econometrics you take, the more you're going to see in matrix and vector form. And when we actually have Stata or R or Python or whatever program we're using do the calculations for us, they really don't use the formulas that we derived in principles or intro econometrics. Those are a rough approximation. They really do it using matrices. And especially in multi-dimensional, multi-variable models, this is really the only way to handle those complications. So we're not going to do the whole model over again in matrices. Where this is going to pay dividends for us moving forward is to really think about the properties of the error term in matrix format. Okay, and a great place to start with that, which is also a fairly simple translation, is to think of the error term as an n by 1 vector, right? So really, we're just picturing the column of data, right, as a mathematical vector. Each element in the vector, each observation in the column of data would represent the error for a given observation, in this case, a given country in our sample. The first thing we might want to think about is, okay, how does this, how would this change how we represent our assumptions? So if we think about assumption 2, it's easy to get this mixed up, right? That's saying assumption 2 was that the average error term should be 0. Well, that, again, that doesn't mean that if we took the average of all the numbers in the column, it would be 0. That would be the average residual within our sample. Really, what it implies is that if we take the expected value of every element in that vector, country 1, country 2, country 3, etc., that the expected values of each element is going to be 0. Every error has its own distribution. The center of each of those distributions is 0. So that's pretty straightforward. But again, it's just a good introduction to thinking about the error as a vector of observations. So in rows, where n is the number of observations in the sample, here would be the number of countries, and one column. Where we really get mileage out of this is in assumptions 4 and 5. The variance of the error term, heteroscedasticity, the covariances of the error terms, autocorrelation. And the way this is, when this is really done, the way this is depicted is in the so-called variance covariance matrix for the error term, where we're going to create an n by n matrix, every element of which is either a variance or a covariance. And it's kind of fun. Let's take a look. The way we're going to do this is take the product of the error n by 1 vector times its transpose. So u times u prime. So here's u, not u, but u, the error term, the column, right, of observations, times its transpose. So that'll be the same observations, but in a single row. And if you, and again, I'm not going to test you on doing the math on this, but the end result's going to be useful. But if you remember doing matrix multiplication, right, when we have an n by 1 column and a 1 by n row, we're taking every pairwise combination, right? So we go u1 times u1, u1 times u2, u3, etc., to un. Then the next row down, u2 times u1, u2 squared, etc. So the result is going to be an n by n matrix of all of those pairwise products. So u1 times u1, error term 1 squared. Observation 1 times observation 2, etc. across. And all of these diagonals are going to be those squared errors. Now, how this is going to be useful is that we are taking the expected value of these products, taking the expected value of every element in this n by n matrix. And it turns out, we can show pretty quickly that that is going to be representing the variances and the covariances. So where we're going with this is that the properties of this matrix will dictate whether your regression has heteroscedasticity or autocorrelation, whether those, the resulting hypothesis testing statistics will be valid. I know, bringing back a lot of memories. So stick with this for another minute. So we're creating this, so we're making the product, creating this n by n matrix of pairwise products, taking the expected value of each element, and what we can show, we've used this before, is that the expected value of a squared error is the variance of that error term, right? Because that's going to be equivalent to expected value of U1 minus U bar squared, which is a variance, right? So all of these diagonal terms, that's the variance of error term 1, variance of country 2 error, dot, 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 all the way down to the end of the sample, variance of country in. We can use the same trick that we are really subtracting off the mean, which is 0 by assumption 2, to show that all of those off-diagonal products in expectation are covariances. So this guy here, expected value U1 times U2, that's the covariance between error 1 and error 2. And what do we expect that to be? Assumption 4 says it should be 0. All of those off-diagonal elements represent correlations or covariances between error terms, which should all be 0. There shouldn't be any of those spillover effects. Right? So I know, we're almost there. But what this is going to give us is a really easy way to think about and express those core properties, right? What does this variance covariance matrix look like? What actually do we need to fix, right? So making that substitution, the expected values on the diagonal, those are the variances. Expected values on the off diagonals, every other term, are those covariances. And substituting in assumptions 4 and 5 give us this, the classical linear regression model variance covariance matrix should be a constant value, sigma squared, all along that diagonal. If that's true, we have a homoscedastic error, constant variance. It should also have zeros everywhere else if we have no autocorrelation. So we can express this as sigma squared times an n by n identity matrix, right? Which that has ones along the diagonal. So all of this is to say that if you see this expressed in any econometric context, that what the author is saying is we are making our classical assumptions, right? That we have no heteroscedasticity, no autocorrelation. Our variance covariance matrix is sigma squared times I. Any deviation from that will mean we need some form of robust standard errors. We need a generalized least squares model, a weighted least squares model, if you remember those corrections for heteroscedasticity and autocorrelation. So the reason I bring this up now, not so much that we're going to be using this in the near future, but when we get to panel data in particular, we're going to see some violations of this that are really going to require us to picture it within this context. Okay? But since we were talking about the classical assumptions anyway, thought I would throw this in there to give us something new to chew on. So work through that, think about that, make sure that that makes sense, where the zeros are, where the constant terms are on the diagonal, match those up with the assumptions. Okay, so off diagonals are 0. That's the no autocorrelation assumption. Diagonals are constant. That's the no heteroscedasticity assumption and the associated violations. Okay, back to the real world. Right? We had our proposed regression example, poverty, education, and international aid. Let's play with it. Let's go get that data. So you may recall one of our favorite data sources is that World Bank open data. So these slides that are posted will have the link to each of the variables. And what we're going to care about in order to download that data straight into Stata is going to be the codes for each. So if you want to play along with this, get back into the swing of things with Stata, remember, if you've just repurchased your access to Stadia, you'll have to reinstall these add-on packages. So you'll have to go SSC install WB open data. And then we can use that command to download our data. So this is the code, the World Bank code for the poverty variable. That's going to be our education expenditure and international aid. And we will use the long option, which will put everything into columns. And this is actually going to give us, we're not going to focus on this now because that's 2 lectures in the future, that this is going to be panel data. So every country across multiple years, we're just focusing on the country by country variation here. But that's what you'll see in the data if you open it up and look at it. And again, you're kind of halfway to getting a data set for, for a thesis project already. You'll have to add some more bells and whistles to it if this is a topic you're interested in. And then we could do some data cleaning. Again, we're just playing around here, but these codes are not super user friendly, right? So we might use that rename command. So we get POV, ED, and AID. So poverty, education, and aid. And we take a look at the data. So we use that sum command to get our table of summary statistics. And going back and looking at the definitions of the data, the units of measurement, the means seem reasonable, but the min doesn't quite seem reasonable. Do we really believe that there are countries with 0 education spending and 0 poverty? Probably not. So we can do a little bit more cleaning. So we might want to get rid of all the missing observations. So drop if aid equals dot. Remember, that means in Stata that it's a missing value. So for whatever reason, that country didn't have data input into the World Bank data set for that year. Same thing with education. And again, I want to get rid of the countries that say that they have no poverty in a given year. I just don't buy it. Don't believe it. So we'll drop those 0 observations. There was only 52 of them, but we can feel a little bit better about our data here. Note that we can have negative numbers for international aid. So if you have a net outflow of aid versus a net inflow, that number will be negative. You might think about removing those countries if you're really focusing on developing economies that are only receiving aid. That's an editorial choice by the researcher. But I'm going to leave it as it is for now, so we can get to a regression. How about that? So we remember, right, it's all coming back to you, that if we type in the command regress, y, x1, x2, in this case, poverty as a function of education and aid, we get our familiar happy little Stata regression table. And so we might want to remember what these values represent. Right off the bat, I'm way off here. Ignore that. Sorry about that. How's for a totally different regression? In the upper right, we get in the number of observations in our regression, which is correct down here, 1,031. So this is, if you had forgotten, this would be a good reminder that this is panel level data, right? There are not 1,031 countries in the world. So each one of these observations is a country year combination. So of the, say, 150 countries that are actually in the sample, each one appears on average, 4 or 5 years. But that gives us an idea of the sample size, right? How big our data set is. And that looks pretty good. Our eyes might wander next down to our coefficient estimates, right? So that coefficient column, these are going to be the B0, the B1, and the B2. So the fact that we have a coefficient on education of, call it negative 3.6, well, remember, what does that represent? Be able to put that into words. That's our marginal effect, our partial effect. Every 1 unit increase in education, so 1% of GDP spent on education more, reduces poverty by 3.59 percentage points. That's a pretty useful use of your resources there, I would say. And that's more or less what we would expect, right? Countries that spend more on education, better educated population, less likely to be in poverty. So that makes sense. The aid variable, difficult to read in terms of its numerical value. So that 6.98 e to the negative 11, remember that's that scientific notation. So it's 11 places to the right of the decimal. So 0.000000000698. That's difficulty number one. And the reason for that, if I read this right, that aid variable is in dollars, right? So that's the impact of one crisp, clean dollar bill handed over to a country. Of course, the impact's going to be very small. But we also know that it is positive, right? So more aid coming in is correlated with higher poverty in the country. Does that mean that aid causes higher poverty, or that it's certainly not helping reduce poverty? Well, for reasons relating to assumption number 3, we're going to need to be careful about drawing that conclusion. But that would be on the face of it, how we would read it, that those two variables have a positive correlation. And this is just a reminder that we can scale those coefficients, right? That if we multiply that coefficient by 1 billion, well, okay, now it's more of a number that makes sense, right? So $1 billion coming in aid is associated with poverty, the poverty rate rising by 0.07, so 7.07 percentage points. Still a very small impact, and still, again, somewhat inexplicably positive. But for our purposes now, just be able to put that into words, scaling it up when necessary, and be comfortable with that terminology. We also want to remind ourselves where those numbers came from, right? So the education coefficient, the aid coefficient, how did Stata come up with those numbers? Well, it used ordinary least squares, right? So it chose the unique combination of coefficients that minimizes the sum of the squared residuals, roughly using the formula that we've seen derived in the past. It's not quite this formula, right, because it's a multiple regression model, but in our mind, not a bad way to think about it. But if that question comes up, where do those coefficients come from? How are they chosen? That's always the answer, right? It's ordinary least squares, minimizing the sum of the squared errors. And we can do a little tour of the rest of the output here, just again, as some reminders. When we see that r squared of 0.09, well, about 9% of the variation in poverty is explained by education expenditure and aid and net aid inflow. What that means, of course, is 90% of the variation is explained by other things. That's another reminder that we didn't get assumption 1 right, that there is a lot of omitted variables in addition to the randomness out there. But for our purposes now, just be able to put that into words, percentage of variation in the dependent variable explained by our model. And then we also have to remind ourselves how hypothesis testing works, right? So every coefficient is going to be given an associated t-statistic and p-value. So I don't include the formula for the t-statistic here. We might want to remind ourselves that it's the ratio of the coefficient to the standard error. So in this case, we are 9.5 standard errors to the left of 0. It's highly unlikely that we would see a value so far away from 0 if the true value was 0. That tells us we can reject the null hypothesis of 0 and say we have a statistically significant coefficient, and that's consistent with a p-value of less than 0.01. So we're able to reject that null beyond the 1% level of significance, meaning beyond 99% confidence. Larger the t-stat, the smaller the p-value, the more significant our coefficient is. Similarly, the F statistic that is automatically generated by Stata is giving us the joint significance of all of the variables in our model, all of the coefficients, which in this case is only 2. The larger that F statistic is, the more significant our coefficients are. And the smaller that p-value is, again, the higher the level of significance, we can reject the null that all coefficients are 0. So it's kind of a moot point in this case because both of the t-stats are individually significant. So variables taken together are going to be jointly significant. But just, again, check that little box. What does the f-stat give us? Our measure of joint significance. Okay. Obviously, there's way more to what we're going to see in our Stata output and everything that goes into it, but that's why it took a whole semester to go through it, right? So just as a quick reminder, hopefully that gets get things going again. So the next installment will start us out in what we'll call lecture 2, delving into really that assumption 3 implication, right? Which is going to be giving us when we can talk about correlations versus causation, when we're going to have biased versus unbiased coefficients, and what we will term the identification scheme of our model. And we'll talk about different sources of bias that we might see within a sample or a given regression. And that'll lead us into how to fix it, where we'll head next. So this will keep you busy for a little bit. There's another video coming up that'll get us started on that next lecture. And then we'll get into the instrumental variables correction next time we meet up. So thanks for your patience and stay tuned for the next installment.